From my YouTube channel, select C++ 17, 20, 23, go to this playlist. From this playlist, scroll down. I assume you have watched episode 127, 128, 129. In our previous episode 129, we learned how to implement, reduce, also how to compare rational numbers. Click Show More. Click this button to download source code from our previous episode. Show in folder, extract, rename 130 rational. Now copy, paste it in your working directory. Show in folder, select CPP 17, 20, 23 from folder 130. Double click reduce.cpp. Ctrl B. We created this source code from our previous episode. If you haven't watched my previous videos, please watch them. Otherwise, you may not understand my current session. Now, Ctrl N. In our previous episode, we created test rational comparison. In this function, I will modify this part. Auto L A L Auto R B R. We defined L R here. Now we don't need this. Also, we can fix this part. L times equal B, or cut, paste R A, or this is equivalent. I will delete. Now we don't need this. Delete. Open up your Clang compiler. CD 130 rational Clang++ CD C++20 reduce.cpp ltbb 12 oc.exe clsc. So we tested this operation. To help you better understand our problem, let me recap. We are comparing two rational numbers. I will denote it left hand side. This is right hand side. So left hand side is a rational 7/15. Right hand side is a rational 11/10. We are comparing these two rational numbers. We factor denominator 15 into 5 times 3. We factor denominator 10 into 5 times 2. So to compare 7/15, 11/10, we factor 15 into 5 times 3 10 into 5 times 2. Then in the 7 we multiply 2. So 7 times 2. 11 we multiply 3. So 11 times 3. We compare these two. Now here, left hand side, right hand side. So L represent 7, A represent 15, R represent 7, B represent 10. We reduce 15, A and 10, B using reduce. After reduction, A becomes 3, B 10 becomes 2. In this expression, 5 times 3, 5 times 3, 5 times 2, 5 times 2. You understand what it means. Then 7 times 2. Here L becomes, we multiply B, so 7 times 2 is 14. So L becomes 14. Here R becomes 11 times 3, so 33. Using spaceship operator, we effectively subtract 7 times 2 minus 11 times 3. This is the result, so it should be less than 0. Now, in our comparison, we never compute 5 times 3 times 2. In this expression, we never compute common denominator. We never compute common denominator. So we prevent overflow in this part. Also, this number, or 1433 can be big number because we have multiplication here. Now, for example, this is 7 times 7, 7 times 11, okay? Then it becomes 7 times 7, 7 times 11, or 7 times 7, 7 times 11. In the same manner, it becomes 7 times 7, 7 times 11. It becomes 7 times 7, 7 times 11, 7 times 7 times 2, 7 times 11. In such case, it becomes huge number. Okay, so we can reduce L and R if both are not 0. So here, right before we compute, if L is not 0 and R is not 0, then we can compute ORO, GG, SED, GCD, L, R. Here, please note very carefully. Then L, GG, R, GG. We can further reduce. Okay, now let's see the result. CLSC. So this result still holds because in this point we reduced 7 times 7, 7 times 11. We reduced using G. SED, C out, GG, GG, SED, and there. Okay, we build again. CLSC, GG is 7. With this information, we need to test with a big number. Now copy this, paste. Test rational comparison with very small number. We have to test with a very small number. Now, auto max long STD numeric limits long max. This is very big long number. STD C out max long max long. This is very big number. I will copy this function, paste it here. I will disable it. Watch it very carefully. Now I will remove this part. Now here we are using long. This is very big number as denominator, and the numerator is very small. This is 1. Also 1. This is 1. Max long V minus 1. So we are using two rational number, STD, C out, left hand side, STD, and there. Paste, right hand side. I will disable this part. Ctrl K, Ctrl C. So we use very long number as a denominator. We print out CLSC. So this is very small rational number. Which one is greater? We can say 1 over 3. Okay, we assume max long is 3. We subtracted 1, so it becomes 1 over 2. If max long long is 3, for example, max long long minus 1 becomes 2. Okay, it means left hand side is less than right hand side. Okay, if this is left hand side is 1/3, right hand side is a half or 1 over 2, then left hand side is smaller than right hand side. It means left hand side minus right hand side is less than 0. You understand what I'm saying, okay? Then I will enable this part. Control K, Control U. Now we test everything works. We rebuild CLSC. So this result should be true. Okay? Because this should be true. So this operator actually means L minus R comparison is less than 0. This is valid operation. Okay, it gives true result with a very small two rational number. Now, in my previous episode, in episode 127, in this episode, I explained the concept of epsilon, also partial order and the total order. So if you haven't watched this video, please watch this video. I will copy and paste the link here. Now double RR equals double left hand side double right hand side SED C out. Okay, you can say I will just copy this is less than 0. This operation, let's see if it holds. Okay, now here I will copy, or this is equivalent to RR. Okay, this expression should also return true. Okay, we are using typecasting from rational to double. Now we build CLSC. Why this message is not displayed? Sorry, we put it in the wrong place. Cut. I have to put it here. Now rebuild CLSC. The result is false. So we cannot compare left hand side rational, right hand side rational. Using this method, we cannot compare. Result is false. It should be true, but false. What's the matter? Why we cannot compare? Very small very small two rational numbers. When we used strong ordering, we succeeded. When we converted to double, it failed. Why? The reason is this. This number is too small to represent using double. Also, this number is too small to represent using double. The difference between left-hand side, this rational number, and the right-hand side, this rational number, the difference or the distance is too small, less than epsilon. Now, here, double left-hand side equals double left-hand side. Copy, paste, right-hand side. I will fix like this. Right-hand side. The difference, std, cout. Sorry. Here, std, cout. This difference is RR. Okay. If we build again CLSD, so if this number is represented as double this number, if this number is represented as double this number, we can increase std, cout, precision. We pass std numeric limits, double max digits. If we build again CLSC, so if we convert this number into double, it becomes like this. If we convert this rational, it becomes like this. There is no difference. So the difference is 0 as double. So it fails. This comparison is inaccurate. These two numbers are too small to represent using double. Scroll up. Here I made a simple mistake. It should be OR operation. In this statement, we divide L by GG, R by GG. GG is the GCD of L and R. GG should never be 0. Now, control home. In this document, std GCD return value, copy, control N. I will paste it here. If both M and N are 0, return the 0. Otherwise, returns greatest common divisor. That means either L is not 0 or R is not 0. Then GG is never 0. So we can divide L and R with GG. I hope you understand why we need this condition. Also, I will explain what is total order or strong ordering versus what is partial order or partial ordering. Understanding total order and partial order is crucial. In this website, you can find three-way comparison operator. If you open this document, you can find partial ordering, 76 occurrence of partial ordering. Okay, partial order is very important. Also, total ordering, 22 occurrence or strong ordering, strong ordering, strong ordering. These things are very important if you want to read such documentation. Working Draft Standard for Programming Language C++. When we discuss ordering, we need one set. S is a set. We need one operation. We represent operation with symbol less than operator. Okay, when we discuss ordering, we have one set and one operator. For any two elements A and B in the set S, A is less than B or B is less than A or A should be equal to B. Okay? Among three conditions, one and only one should hold. I say 1, 2, 3. So only one and only one condition should hold. It is called comparable. If there are elements that does not satisfy this condition, we say incomparable. If all elements of the set S with respect to the operation satisfies the above condition, we say the set forms total ordering with respect to operation less than. Otherwise, the set forms partial ordering. The set of real number forms total order with respect to this operation, but the set of f floating point number has incomparable elements, so floating point number forms partial ordering. Both integer z and rational number q form total order, or in programming it is strong ordering or SED strong order. In this case, SED partial ordering. We said the set of f or floating point number has incomparable elements. Now, in this case, left-hand side right hand side. They are obviously different, but in real number, they are actually incomparable. We can change this value. For example, we minus 100. We build again CLSC. It is still false. There is no difference. Now 1000. The difference is 1000. We build again C. Now there is difference. Now it works correctly. Okay? The difference between left hand side and right hand side is greater than epsilon. The difference is greater than epsilon. Now it holds. So the result is true in both cases. True, true. But the difference between these two numbers is too small, such as 1. Then these two numbers are not comparable. Okay? Left hand side, right hand side, they are obviously different as rational number, but double, they are not comparable. That's why floating point number forms a partial ordering. Now, with such information, we can overload operator for rational. Right-click, go to definition. I will arrange side by side. In this file, cpp rational.h, Control F, find the spaceship operator. Spaceship operator is defined 3 times, not 5. Now, close it. I will remove Ctrl K, Ctrl C. So I commented out. I will help you understand how to define this function. It is friend function. Context for SED, strong ordering. Operator. This is spaceship operator. Constant, rational, left hand side, constant, rational, right hand side. So we have to return strong ordering because we define rational number. Now, if left hand side m denominator equal to right hand side m denominator is equal if left hand side m numerator equal right hand side m numerator, then left hand side and the right hand side, these two rationals are equal. So we return SED, strong ordering, has a member equal. Okay? Else, if left hand side m numerator is less than right hand side m numerator, then we return left hand side is less. Else we return greater. So when denominator of left hand side and the right hand side are equal, we can quote like this. The reason I quote like this is for performance. Else, it means denominator of left hand side and the right hand side are different. In such case, we use this mechanism. So copy here, paste. Okay, this step. Then we reduce, paste. Then we need this, paste. Like this. I will remove the message. Now we need this operation. Like this. I will simply fix like this. Now, in this part, we can use this operation. Or I will simply use this code. Now, go up. Instead of, I will use this code. Copy, paste, uncomment. I will make it bigger. We learned this does not work. Okay, we learned this does not work. Instead, cut, paste. Now I put DIFF. Okay, then everything is fixed. So if DIFF is less than 0, we return strong ordering less. Greater than 0, we return greater. Else, we return equal. Okay. Actually, this part never executed. With this, we test our comparison. Now scroll down here, void test rational numbers. Copy this function name, paste it here. I will disable. We need using namespace cpg rational numbers. Rational a, for example, 7 times 7 over 10. Copy, paste. 11, 15. This is B. std cout. A, std, and there. Copy, paste. B, std cout. A less than B, A less than B, std, and there. Copy, paste. A greater than B, copy, paste, A equal to B. Now we test this function. If it works, we rebuild. Sorry, this is not reduce. Control home. This is reduce adjusted. In this function, we don't need try catch because it does not return exception. I will unindent like this. This function is reduce adjusted. So I will copy. Let's rebuild. 360. Go 360. This should be reduce adjusted. I fixed. We rebuild. CLSC. So A is less than B. True. All others are false. It's hard to read. Then we can make it simple. For example, 1, 3, 1, 2. CLSC. B is greater than A. Or we can say SED C out. A minus B, A minus B, SED, and there we can test our computation like this. CLSC. So A minus B is negative minus 1 over 6. So this is true, correct calculation.